Okay, continuing on, we want to sketch the graph of r equal the cosine of theta. We know the cosine of theta is a circle wrapped around the positive x-axis. The only thing the square root will ensure is that the amplitude is really not 1, the square root of 1. In this case, it doesn't make much of a difference. And all what I'm looking at is a circle with a radius of 1. Let me use a different color so we can see it better. Here we go. A circle with a diameter of 1 wrapped around the positive x-axis. And what we want to find this area. So if I draw my arrows, I rescaled that. I should have rescaled it even more. Maybe even better. Not that it's hard to see actually here. So if this is the graph, let's say that is 1. So it's a circle with a diameter of 1. There. And what I want this area right here. And I would know that the area will be the integral. So if I run my arrows from 0, of course I could run from negative pi over 2 to pi over 2 and get it over with. Or I could say let's run from 0 to pi over 2. And the tip of the arrow is really nothing more than the function. And if I multiply it by 2, that will do the trick. Next problem on the list. Okay. There we go. If I am to look at r equal to a unit above, r equal 3, a unit below, r equal 1. So from this I know that there is no inner loop. A graph of a sine wave starts with the origin. This would be 2 pi, pi, pi over 2, and 3 pi over 2. I know what that graph looks like. I know the shape looks something like this. At 0, I am at 2. Increases. By the time I hit pi over 3, I am at 3. Decreases back. By the time I hit pi, I am at 2 again. Pi 2. Oops, let me make it smooth. Keeps on decreasing. By the time I hit 3 pi over 2, I am at 1. So the graph looks something like this. Well, I want to find this area. And the way to do that is to say, well, here I have so many options. Any one of them will do. I could run in positive, I could run in negative. It's up to you how you want to do this. I could say the area will equal. One way of doing this is for me to run from, if I start at 0, you could do that. If you start at negative pi over 2 to pi, that will do the trick, because you notice you're running straight up. So you could say, let's start from negative pi over 2 to pi over 2. 1/2 r squared d theta, and r is 2 plus the sine of theta. A couple of ways you could do it. You could say, I'm going to run from 0 to pi over 2, that will work, of 1/2 2 plus the sine of theta squared d theta, and then add to it the integral, say, from pi to 3 pi over 2 if you really want. It's up to you. And multiply the result by 2. You could run from negative pi over 2 to positive pi over 2. That will work as well. So many options to do. I suggest you make use of symmetry, especially for what's to come. And here, I know this should be a 4-leaved graph, and I know I'm going to square root both sides eventually, getting a 2 instead of a that saves me time. And if you didn't see that, not a problem. Like I said in my previous video, not of this section, of the previous section, you could ignore that and rescale the graph after. Again, it doesn't really make much of a difference. So here we're going to go up 4 units. Let's say that's 2, that's 4. And negative 4. And a cosine wave starts at the origin. A cosine wave starts at the amplitude, runs down to that amplitude, back to the starting point. This is 2 pi divided by 2, which is pi over 2. And this will be pi over 4. So here, I would add my auxiliary lines. I need them at the pi over 4. Here they are. This graph, at 0 I am at 4. Decreases. By the time I hit pi over 4, I am at 0. So make sure you hit 0 before you reach that. And you're done with the graph, because you know this is supposed to be, without the square, a 4-leaved graph, which means they're 2 pi over 4 apart. So if this is 0, 1 pi over 4, 2 pi over 4, it's going to happen again. Another 2 and another. So generally, without the square, that's what you have. A graph that looks like this, except since you do have a square root, you know that's actually a 2. You could relabel that. That's not a problem. That's 2 and that's 1. And you know that it cannot be negative. We know it's negative between pi over 4 and 3 pi over 4. So this part of the graph really resembles this part, and this graph is symmetric, so that part is not there. So the actual area is nothing more than those two. I would say the area is the integral. If I run from 0 to pi over 4, that'll get me half of the first leaf or petal of 1/2. The square of r is already for the cosine of 2 theta. No need to add the square because that's what it was. And you multiply that by 1, 2, 3, 4. That'll do the trick. Of course, you could do from negative pi over 4 to pi over 4. Just be careful. The limits on the integral must be in increasing order. Otherwise, you'll get area to be negative, which is not allowed. And again, I'm not working those out assuming you can integrate that, because we already did integrals of sines and cosines and trig functions, if you remember. Now the next problem down. This is the one with the loop, so let's get that out of the way. And here we are. We go to r equal 1. I just need to bring that down just to see it better. There we go. And we go up 2 units and down 2 units. So we have r equal 1. 2 units above, that's r equal 3. 2 units below 1, r equal negative 1. And a graph of a sine wave starts on the amplitude and the origin, runs up to the amplitude, back down, and there it is. And we already know how this goes. I need to know what this point is and this point is to figure out where the inner loop matches. You set that equal to 0. That means the sine of theta equals negative 1/2. A reference angle of that, the reference angle meaning you ignore the minus, sine of pi over 6 is 0, but sine is negative, Sine is negative in quadrants 3 and 4. In quadrant 3 it is 7 pi over 6 and 11 pi over 6. So I know which lines I need to add. I need to add those two, the pi over 6 and the negative that. Now the graph of a sine wave starts at, so we know the shape looks like this. That's, again, a rough graph, doesn't have to be exact. Well, at 0 I am at 1. At 0 I am at 1. This increases. By the time I hit pi over 2, because that's 2 pi, that's pi, pi over 2, and 3 pi over 2. So by the time I hit 2 pi over 2, I am at 3. There's pi over 2, 1, 2, 3. Comes back. By the time I hit pi, I am at 1. There's pi, there's 1. Now, I am going to run and hit 0 by the time I hit 7 pi over 6. There's 7 pi over 6. This is going to come down and hit 0 right there. Between pi over 6, between 7 pi over 6 and 3 pi over 2, r is negative. You're no longer in this quadrant. You are in this quadrant. And by the time I hit 3 pi over 2, I am at negative 1. There's 3 pi over 2 and there's negative 1. But that starts from this line. Right there. And I know it's symmetric. It's going to come back and hit 0 by the time I hit 11 pi over 6. And between that, there. Now, I want to find the area it encloses. No matter what I ask about this graph, whether I say find the area inside of the big loop, outside of the small loop, if I say find the area of the inner loop alone, no matter what I say, you're going to have to really figure out those 2 points. Area is going to be the integral. Oops. Now, observe what happened when I draw my arrows. It's going to be the integral. If I start at negative pi over 6, there's negative pi over 6. My arrows are going to run to the curve, to 0. Keep on running. Do you see it runs from the origin, so it's already including the inner loop? If I run all the way to pi over 2, I just got half of that graph. And now I'll put 1/2 r squared, 1 plus twice the sine of theta squared d theta, and I multiply that by 2 and I'm done. Again, the integral from 0 to 2 pi will not work because you will retract that inner loop. I'll talk about that when you ask for this on the homework, and if you don't, I will talk about it. Now what? I want the area inside of this circle wrapped around the y-axis with a diameter of 4. So, a diameter of 4. Okay, you get the point, but let me try and make it perfect if I can. Here we go. Okay, and inside of this, and I want it outside of this other circle. Let me use r equal to. I just want to shrink that a bit. So r equal to, I know is a circle. Almost. There we go. Okay, so now kind of hard to match those. Okay, so the area that I would like now, area inside of the big, outside of the smaller one. So I'm looking for this area. And that's where these graphs become essential. Now, one thing I need, I am aware that I need to know where this point is. because I do know when I draw my arrows from 0 there's nothing there. I know I have to subtract, and if you notice all throughout this region area is the integral. I'm running from this angle to pi over 2 of 1/2, and how does it work? I subtract the radii, and how does it work? It's the purple minus the orange. How am I going to figure out where that point is? I'm going to take for the sine of theta and set it equal to 2. That's how we figure out where the graphs intersect when you solve them as a system of equations. We know the reference angle is pi over 6, so we know this is pi over 6. And there it is. That's half of it, so I multiply it by 2, and that takes care of business. And that's why graphing is extremely important in these cases. If I look at the next problem on the list, I want an area inside of 1 plus the cosine of theta. Well, I know how that graph looked like. At 0, I am at 2. So I'm going to let me eliminate. How would I do that? There we go. At 0, I am at 2. This, by the time I hit pi over 2, so I know this graph looks something like this. Oops. Like this. No loop. At pi over 2, this will be 0, I am at 1. At pi, this is going to be 0. And the graph is symmetric. There it is. I'm just going to expand that part a bit more. There. And this graph, I am aware that this is at 0, I am at 2. At 0, I am at 1. I'm sorry, 1. This graph is wrapped around the negative x-axis. At pi over 2, I am at 2. At pi, this will be 1, that will be 3. There's pi. Oh boy. That I didn't pay attention to. My mistake. Okay, I'll add another. You ruined it. Okay. I didn't see that coming. And it's symmetric. I really messed up on this graph, but it's okay. Here we go. Find the area inside of the purple outside of the purple outside of the green. That would mean this part. This is the only part that I need. Well, we have a problem again. Oops. Not this part. Outside of the green. This is the green. Outside this part. Symmetry plays a big role here. So if I take my arrows and I know from 0, I'm going from the green to the purple until I get to this angle. I need to know what that angle is. So I know the area equals the integral. If I run from 0, I'm going to multiply by 2 because the top and the bottom. I need to know where that angle is. I'll put it right there. Of what? 1/2. And now in this case, the outer is the purple minus the inner is the green. d theta. And now comes the tricky part. Where does 1 plus the cosine of theta equals 2 minus the cosine of theta? That's when 2 cosine of theta equals... Oh, I messed up big time. equals 1. No, I didn't. Cosine of theta equals 1/2. And the reference angle, cosine equal 1/2 at pi over 3. So I got this to be pi over 3, and I got the problem. And there it is. And if it's not a standard angle, use a calculator, but that's not going to be the case. And how about the last part? This is a four-leafed graph. I know that already. Let me use purple on it, or pink. At 0, I am at 4. At pi over 4, so I know I've done this a few times, hopefully, and you're comfortable with that as I am comfortable with it. If not, you could sketch a graph of this and figure out these points. At 0, I am at 4. At pi over 4, that's going to be 0. So pretty much that's how the graph looks like. This is a four-leaf graph. 2 pi over 4 apart. This time there is no square, so it's all 4 pieces. Now I'm looking at r equal 2 is a circle with a radius of 2. Right there. So what I want the area that's common to both. What's common to both would be this part. That's the area inside of both. There are 8 pieces altogether. If I could find a quarter of them, that would be more than enough. Well, we have a small issue. Let me show you what that issue is. And that's why the graph is important. There we go. So if I run my line, I know they intersect there. But I notice if I run from 0, I'm running to the green. That's not a problem. To this part right here. So let me get that out of the way. Area equal the integral from 0 to, once I find that, I'll fill it in. That's 1/2 the green function. That is 2 squared d theta. Plus, once I get to that angle, if I run to pi over 4, I'll notice that my arrows now are running, and let me shrink that a bit so you can see it better. My arrows are running now to the purple. So it looks like this if I expand that greatly. It looks like this, and the green looks like this. And when I'm talking about the area inside of both, there's a portion of the graph that really runs to the purple. And that's where I put 1/2, and the purple is, or the pink, for the cosine of 2 theta. And that's going to run to pi over 4. So the key is figuring out where this angle is, and that's when you take 4, the cosine of 2 theta, set it equal to 2. Cosine of 2 theta equals 1/2. I have a reference angle of pi over 3. But it's not cosine of theta, it's the cosine of 2 theta. So if 2 theta equal pi over 3, that means theta equal pi over 6. So that's pi over 6. And if I take this and multiply it by 1, 2, 3, 4, 5, 6, 7, 8, that will do the trick. And that will be my area. And that takes care of this section.